So it's a lovely evening, and I thought of recording a video on gravitational physics, particularly the general theory of relativity, Einstein's theory of gravity. So a lot of people almost everyone's heard about this. It's very famous, but very few people actually understand it. And the problem with the popularizers of science is that they never go into the depths of the theory, and they just give you a very vague understanding of what it means. So people will tell you that according to Einstein's theory, space-time is a fabric, and masses are like a heavy weight on the fabric which curves the space around it, and that's what relativity says. Now, while that's true to some extent, it's not completely true, and because it's not very rigorous, you won't appreciate the beauty of the mathematics behind the theory. And because if anyone tries to get a good understanding of the metric tensor, what's a manifold, if you Google stuff, you just get very complex looking answers which just lead you deeper and deeper into the rabbit hole. So if you Google what's a metric tensor, okay, if you Google relativity, it'll tell you something about the metric tensor. To understand tensor, you Google, you like click on that, and it'll tell something about manifolds. And so it just never stops, and people get frustrated because no one will give them the information needed in one place without going like completely into mathematics or being completely trivial. Like, no one will tread the middle path. So I personally have faced this frustration. In class 11 and 12, I didn't know. I was just learning calculus, and I didn't know a lot of linear algebra. Like, we just knew matrices. So it was very hard for me to understand. I really want to learn the theory of relativity, and it was really hard for me to, like, it was frustrating because I could not learn it. So it took me about 2 years of self-teaching myself in university, in college. I had to start with after we started learning linear algebra, I had to teach myself a bit of topology to understand manifolds and Hausdorff spaces and so on, and then I had to dive a little bit into differential geometry to understand how it works in how the maths works in Einstein's theory. So today's video, the goal is to give a concrete understanding of what the metric tensor does in relativity, what a manifold is, and how these things look mathematically, and what each of those terms mean. So you would have seen something like the Einstein field and the Einstein field equations. You have terms like G mu nu, T mu nu. You don't know what it is. Like, you just see it's some random term and you give up because it's just too hard to understand. It's actually not. If people can teach it properly, it's not hard to understand. G mu nu is the metric tensor, and T mu nu is the energy momentum tensor. So today we'll focus on G mu nu and what it looks like. So let's get started. So first up, let's talk about the basic idea of the general theory of relativity. It says that you have masses, and masses bend and warp the fabric of space-time. That's an explanation everyone's heard, but I just wanted to get that out of the way. Now, what does it actually mean? It means that you have masses, and space-time are not separate. They are one entity, and whenever you put a mass, the the geometry of space-time changes. That's all. Secondly, what is the metric? Now you have this term in Einstein's equations called G mu nu. Now people normally get lost when it comes to metrics. So a metric is just like a map, sort of a map. So whenever, let's say you take a normal map, a map of the world, a map of the earth. When you take a map of the earth, you would see that the map has a scale at the bottom. It says that it's actually a ratio that says that some distance on the map is equal to some distance in on the actual earth. So it'll be, let's say, 1 is to 150,000. So that means that, let's say, 1 centimeter is equal to 150,000, whatever the unit may be. So I'm just giving an example. So that is what we mean by a scale. Now, if you ever look at a map closely, you would know that it's not very accurate. As in, it denotes, like, it shows countries like India, then let's say the Middle Eastern countries, then some African countries pretty accurately by size. But as you go up or down, you would see that Greenland is bigger than Africa, and Antarctica is probably bigger than, like, probably bigger than Asia. Now we know that actually they aren't that big, but we get these errors. So when you because you're transforming something which is 3D, the world is close to a sphere, onto a 2D map with just one scale, you won't get very accurate readings because the geometry is bent and you're trying to flatten it out without changing the scale at every point. So if we want a more accurate version of a map, we need to change scales as we move up and down, right? Because the problem is that we are using the same scale for the part near Greenland as we're using for, let's say, the part near India. But India is equatorial, like it is close to the equator, so it's not very distorted. But Greenland, because it's very far, it's like the Earth closes in at the poles, so it's very distorted, and you get these weird anomalies. If you want to overcome that, we need to have a scale at every point. If we had a scale at every point, then it would solve the problem. Greenland would also be accurate in terms of size, and the Earth, I mean, and India would also be accurate in terms of size. So, if we were to introduce a scale at every point, that is something like the metric. The metric is basically, the metric tensor is sort of like a scale which represents every point on this fabric of space-time. So whenever you put a mass, it distorts space-time. So how much to distort by, all that is given by the metric tensor. That's a analogy. That's a very good analogy, which I can say. I would say you can't simplify it more. This is the best analogy I can possibly give. So you have a curved surface, and because it's curved and I want to imagine it to be flat, I need to transform, like I need to change the scales. These scales are changed by the metric. Now again, when I say space, there are a lot of words floating around which might not be helpful, but I'll just say it in case anyone's interested. We have something called a Minkowski space, we have something called a de Sitter space, and something called an anti-de Sitter space. So what does it all mean? Minkowski space basically just means it's a flat space. So there is no curvature, it's flat like a table. De Sitter space means the space has positive curvature. So what do I mean by positive curvature? It is bent, it is curved like a sphere, like a basketball or a football. It's curved like this. That's de Sitter space. There's something called an anti-de Sitter space, which is negative curvature. So space is bent like a saddle on a horse. That's the shape of space. So these terms just might come in Minkowski, de Sitter, anti-de Sitter. So I just want to get that also out of the way. Okay, now we've cleared this up. Now what's a manifold? Now I'll explain on the board as well, but let's just talk about manifolds in a little trivial sense. If we take the Earth, and the Earth is a curved surface, as we spoke about. The Earth is very close to a sphere. Now, as we said, there are there are flat spaces, there are curved spaces. So if we look at the Earth from space, like let's say if we look at the Earth from Mars, it looks to be a ball, like a curved surface. If you're standing on the Earth, let's say I'm standing downstairs on the road, and I look at the geometry around me, the Earth looks very flat, like it looks like a plane. Now, a manifold is just that. A manifold is something which is curved on bigger scales, but locally it's Euclidean. Now, Euclidean is just a fancy way of saying planes are flat. Non-Euclidean geometry has curved planes. So, because the Earth looks pretty flat on small scales, it's Euclidean. So, that's a manifold. A manifold is something which looks curved on a bigger scale and flat on a smaller scale. That's a manifold. Now, a manifold, there's some amount of maths jargon which we'll again talk about on the board. The maths jargon is that a manifold needs to be something called a Hausdorff space, and it needs to be second countable. Now, these are fancy maths words which again I'll explain, but let's just think about what they mean. So, when we talk about a mapping, so if we map a linear map is basically a vector space, and it preserves, linearity. If we were to map more than something more complicated than a vector space, that would be a group. So a group homomorphism preserves the group structure. So a vector space preserves the linear structure, a vector space structure, and a group homomorphism will preserve the group structure. Now, what is more complicated than a group? It is something called a topological surface. So, a topological surface will preserve a topology which is continuously differentiable and it's an open set. Now, what do these things mean? Again, it's a lot of maths, but it just means that it has to be the sets have to be open. Means if I have two elements, the two elements should not be intersecting, they should be separate, okay, like open sets. So that is an open set. This open set is called a Hausdorff space. That's just math jargon for those people who are really interested. So this is a Hausdorff space, and a manifold has to be a Hausdorff space and second countable. Second countable means integration should be defined on the mapping. So if you have a Hausdorff space and integration is defined, it's a manifold. Okay, now I think that's enough of the basics. Now let's get to the actual juicy stuff of the metric. Okay, so let's now get to what the metric tensor is. So we have metric tensor denoted by the terms G mu nu. That's just the notation. Now let's again bring back our analogy of maps. So on the map you have latitudes and longitudes, and they form this grid, right? Now if I want to map this grid onto a spherical surface, I need to, let's say I have a ball, and it's like putting a paper on a ball. So these angles and these lengths will contract or get distorted. So there needs to be a transformation. A transformation, as some of you might have heard, a linear transformation is something which changes, the coordinates on a linear structure like a vector space. Here we have a topological space. So it has to, work with the manifold and change the coordinates on the manifold. So as we say, space-time is a smooth manifold. So we've talked about what's a manifold. So space-time might look something like this. It might be curved, but it's always smooth. So now, if I want to map this onto, let's say, a sphere. So these are latitudes and longitudes, right? So this has to sort of warp onto this. Now this will have some x coordinates and some y coordinates, right? Now if I want to first talk about the 2D metric. So let's say I have a map and I want to change stuff on a map. That will give me the 2D metric, right? So it's something called a 2D metric. We're talking about 2 dimensions first. So the 2D metric will serve as a transformation for 2-dimensional surfaces, and it will be something like a flat sheet of paper. Now, when you talk about transformations, they have to be something like a matrix. So we call them tensors, but they look like matrices. So the 2D metric, for example, looks like this. So you have the term sine squared y, you have the term 0, you have the term 1, and you have the term 0. Now, what do each of these terms mean? We'll come to that. So let's say I have x coordinates and I have y coordinates. When I map it onto this, there will be, this is the equator, let's say. So, and these are the poles. So, when I map onto it, the poles are getting contracted, like everything is squishing up onto one point, while on the equator, it's staying the same. So, to sort of think of it mathematically, on the equator 1 remains 1, so it's staying the same size, so it's not changing by any amount, while on the poles they're becoming, like, some x is becoming 0. So we need to come up with a transformation which makes this true as we move up and down the map. Also, this is for the x part. As you move, like widthwise, that is on the x coordinate, this is happening. On the y coordinate, though, stuff isn't actually changing, because see, even if you go to the poles, length isn't contracting. Only the width is sort of contracting into this point over there at the north pole or the south pole. So y is just staying y. So y is staying itself throughout the map. So y isn't actually changing. So to get this transformation, we can use this matrix. How do we use it? Well, this one will denote this part. So it'll say that whenever I'm changing the metric, whenever I'm applying the metric and changing the topology of the space of the manifold, what will happen is, when, let's say you take some point, this will change according to the square of the sine value of the y coordinate. So if my y coordinate is, let's say over here, let's say this angle over here, the angle is, I'm taking some value pi by 2. So sine of 90 is 1. So this will become 1 squared, which will be 1. Now if I go over here, if the angle is, let's say, pi or 0, this will become 0. So it will contract onto one point. So this is a 2D metric. So this term changes the x part. So the first term changes the x part. What does this term do? This term talks about how the y part changes. And as I said, the y part doesn't really change. It stays the same. So this will be 1, because anything into 1 is itself. So this is 1. This represents the change of angles. Now, because latitudes and longitudes are all at 90 degrees on a flat map, I'm not going to mess with this. But if you have a different version of a map, let's say something like the Robinson map, which has latitudes and longitudes, not at 90 degrees on a flat scale, then to make it 90 degrees on the sphere, I need to add some term over here as well. But this talks about the angle. And this term over here is just for symmetry. It's called a symmetric term, which we don't really need to worry about right now. So these are the most important terms, and this talks about the angles. Now this was 2D. As we said, space-time, if you add, is a 4-dimensional manifold, because you have 3 dimensions of space and 1 dimension of time as we understand it now. So this works for flat maps and spheres, which are 3D, like 2D into 3D. Now we can't really comprehend 4-dimensional structures. We can imagine them mathematically, but for us to work with them, we need to make it into a 3D structure. So let's talk about the 3D metric. So if we have a 2D metric, it's a 2 by 2 matrix structure. So a 3D metric will have a 3 by 3 matrix structure. So if we draw a 3D metric, it'll have some terms like this, like let's say it'll have 9 terms basically. 1 2 3 4 5 6 7 8 9. Now I'm just explaining it based on how a matrix looks like. So as we talked about in the previous one, the diagonal elements talk about the axes. So if we have a 3D structure, these are the x, y and z axis, right? So you have, let's say, y, x and z. Now when I want to change all three of them, I'll need 1, 5 and 9. This will tell me how to change the lengths of the axes. Elements 2, 3 and 6 will tell me how to distort the angles. These angles, alpha, beta and gamma. So x and y, let's say alpha, let's say y and z, this is beta and this is gamma. So 2, 3 and 6 will tell me how to vary alpha, beta and gamma. Now let's imagine again as we imagined for a map. So this time, instead of a 2D structure, we'll take a 3D structure. So a 3D structure, we can take something like a cube or a cuball. Now if we break this up into squares, we get what we want. So we need to break this up into smaller, infinitesimally small cubes actually. So this will be some infinitesimally small cube. Again, the same logic applies. If I want to apply this onto something one dimensional higher, that is with time, my Pythagorean triplet will not work. So I can't work with Pythagoras' theorem. I need to work with the cosine law, the law of cosines, because I'm transforming from right angle triangles to acute angle triangles, or maybe obtuse angle triangles, depends on the curvature of space. But because these triangles are not right angled, I need to change from the Pythagoras theorem into the law of cosines. So that is the explanation behind these terms basically, that your Pythagorean triplet no longer holds true because the angles are changing. It's no longer a right angle triangle of a cube. It might be bent, so it might become an acute triangle or an obtuse triangle depending on the curvature, and so I have to apply the law of cosines. And this stays the same, that if you have if I'm let's say bending this, let's say this cube is becoming something like a parallelepiped, then this will give me how much I would distort the x-axis by. This will give me the y-axis part, how much I distort the y-axis or contract or expand. This will give me the z-axis. These three will tell me how much should I change the angles. So the cube might become something like a structure like this. So this is the gist of what a metric is. So after this, we are ready to handle general relativity. So this gives you an intuitive picture of what the metric actually does. The metric is just a fancy word for a scale, and the manifold is just a fancy word for a smooth surface. So I guess that's it. Thank you.